Okay, this is Colum Joyce. This is my final CHEM culminating assignment, and I'm going to be talking about transesterification and biofuels. So I got a lot to talk about, so let's get started. So the process of transesterification is when triglycerides, which are animal fats and vegetable oils, react with an alcohol group. This results in glycerol and methyl esters, otherwise known as biofuel. So the structure of the molecules that are included. So we have fatty acids, which look like these. As you can see, they got a long hydrocarbon chain with the carboxyl group at the end. And in this carboxyl group, there is a hydroxyl group. And then we also have esters, which you'll notice have a similar hydrocarbon chain with that alkoxyl group. And then the hydroxyl group is replaced with a methoxyl group. All right. And then we have triglycerides, which are these three fatty acids grouped together with that green glycerol chain at the end there. Okay, so what structures equal what properties? So the functional groups are most of the properties of these molecules. We have the hydrocarbon, which is stays pretty stationary throughout the reaction. It looks like this. This is a saturated hydrocarbon. So as you can see, all those carbons are pretty happy because they're fully saturated with hydrogens. So they're not really going to react too much. And then we have the carboxyl group, which is at the end of these hydrocarbon chains here. And those are what are going to react and really push this reaction forward. As you can see, there's a pi bond, a double bond there. So that's going to break, which allows the carbon to take on another group. And there'll be a leaving group from that carbon when they reattach that oxygen there. And there's also a lot of high electron density here because you have the hydroxyl group as well as the double bond with oxygen there. So a lot of electron density just causes charges to mix and things will happen. So this is usually the nucleophile in the case because of that high electron negativity of the oxygen as well as the carbon taking things on. Then we have the hydroxyl group, which is included in the carboxyl group with some of our other molecules, and it looks like this. Okay, it's very reactive, electronegative. Alkyl group, not very reactive. Glycerol backbone, not too reactive. They stay pretty much the same. Okay, so what we start with in transesterification. We start with triglycerides, which I showed you, alcohol, like that, and our catalyst, sodium hydroxide. What we finish with is glycerol, which is this little propane chain. If you turn that sideways, we just replace those hydroxyl groups with fatty acids to make the triglyceride, and methyl esters, which is the fatty acids that were cut off of this glycerol backbone. So they look like that. As you can see, those are three separate, not connected fatty acids. Nice. Okay, so here's the mechanism that gets them there. We're going to talk to Professor Colum here. Let's see what he has to say.
I'm going to be explaining the mechanism behind transesterification. I've done some good housekeeping by already drawing out all the molecules in an easily usable form. Now I'm just going to draw in the electrons as well as the mechanism. Okay, so our starting products, we have alcohol and triglycerides. And then our final products, we have glycerol and methyl esters. Okay, so the catalyst that helps them get there is sodium hydroxide. So let's get started. We draw that. So if you look at the polarity here, you have positive here. This oxygen is going to be negative. This bond between hydrogen and oxygen is going to break. This oxygen is going to uptake those electrons. And then this oxygen is going to take that hydrogen right there. So draw that there. So that is going to create H2O as well as methyl oxide. So I'm going to draw in a methyl oxide right here. So we have our methyl group right here, and then we have the oxygen with 6 electrons now, so it's a very negative charge. And then we've got our triglyceride molecule right here. As you can see, it's 3 fatty acids connected by glycerol backbone. The only thing you're missing from this glycerol here is those 3 hydroxyl groups. So I'll just have you note that. And then these fatty acid groups, these lines of this hydrocarbon chain is going to be shorter or longer, it's all dependent on the fatty acid you got. So this methyl oxide is going to react with these carbons right here. Carbons are going to act as electrophiles, so they are going to accept these electrons right here. The ratio of alcohol to triglycerides is 3 to 1, so there's going to be 3 methyl oxides for every one triglyceride. That's what's needed to make the reaction go towards the right. But they usually use 6 to 1, like the Chatelier's principle, to push it further. So there's going to be 6 at every one of these. See, so I'm just going to draw this happening 3 times. 1, 2, 3. So drawing that time. Okay. So as you can see, there's an intermediate stage. It's not going to go exactly to glycerol and methyl esters. So that's what I'll take you through right over here. So we have the intermediate stage. We have the methanol reacting with the sodium hydroxide, giving us the methyl oxide and H2O. So the methyl oxide has reacted, the oxygen has reacted with that carbon there. There you go. And then it's going to give you this intermediate structure. I just drew the triglyceride as 1/3. It's a glycerin backbone as a word here, so just as it's a lot more. And here you go, you're going to have this carbon connected to 3 separate oxygens. This pi bond is broken, so this oxygen took those electrons. Pi bond broken, you have single bonds all around here. So this guy's going to have 6 electrons. This is. Okay, so this guy's not very happy because he lost pi bond. He wants that back. So what he's going to do is he's going to throw those electrons back on top of that single bond, creating a pi bond. As you can see down here, he got his pi bond back, but at the cost of this guy's bond breaking. So he's going to uptake those electrons. This bond is broken right here, and that's how you get the glycerol backbone breaking away from the triglycerides. And as you can see, you're left with 3 fatty acids. So you come down here, this methyl group right here, or methyl oxide group, goes down, and you just have okay. So here, so the glycerol is still complete. We have the propane chain right here, and then you just have the oxygens sitting on the outside of it. So these are still extremely electronegative. They're going to have 6 electrons on the outside of them, right there. So these are all negative. And they're going to be the nucleophiles in this case. It's going to accept the electrons. It's going to be one of the hydrogens off oxygen here. So we're going to draw these in here. We're going to start the electrons, draw them off that hydrogen there. So we're going to do that 3 times. So this oxygen bond will be broken. This oxygen is going to accept those electrons on all 3 of the waters. And then you're going to have your glycerol being completed with these hydroxyl groups right here because they got this hydrogen there. Okay, so we are left with a hydroxyl group from the water, and we still have sodium hanging out all by itself. So that is the catalyst sodium hydroxide. It's going to be reformed and it can be collected. And then we have our glycerol, which has been completed. Very dense molecule, so that's going to sit at the bottom of the barrel or whatever you're forming this in. And then we are left with our methyl esters here. Just 3 fatty acids here. You got your carboxyl groups on the end here. Our little methyl groups added, and then your 3 fatty acid chains. And those methyl esters are actually called biofuel, and that's what you're going to put in your car seat.
Awesome. Thanks, Professor Colum. Couldn't have said it any better myself. So let's talk about why the reaction happens on a small scale. So we call this the nature of the reaction. And this is due to the functional groups that I talked to, and most especially the electronegativity, as well as the electron density that we see mostly in that carboxyl group at the end. The triglycerides and the fatty acids have those hydrocarbon chains, but it's mostly the things at the end of the hydrocarbon chains that make the reaction go forwards because of the electron density. So why the reaction happens on a large scale, and this is the nurture of the reaction, this is what factories can change to make the reaction make more of the products that they want. So what drives it forward is Le Chatelier's principle. And that's because this is an equilibrium reaction. So if they increase the concentration of the reactants, that will drive the reaction further to the right, making more products. So what they do is they have the 3-to-1 ratio, which is needed for the reaction to go forwards. And instead of doing that, they do 6-to-1. So that increases the reactants, creating more products. As well as using catalysts. And they also run the reaction through twice, removing some of the products. So they'll remove glycerol, decreasing the concentration of the products, which will further push it further towards the right. Okay, so why do we care about this reaction? We care about it because of the substance it makes, these methyl esters. It takes everyday waste products, for example, things that we normally throw out, like vegetable oils or bacon grease or just other animal fats and oils, and it turns them into a fuel, more specifically, a biofuel that is renewable and is not a fossil fuel. It can be used to power everyday things. This is what I find really cool, is that we don't need new inventions to use this fuel. We can just use our traditional diesel engines as well as other motors, like cars. In fact, the initial fuel used in a diesel engine was vegetable oils, but they found the petroleum oils work better at lower temperatures because it didn't clog up and saturate. Also, it can be used for heating houses, creating electricity, which in turn can be used to charge your phone, charge this laptop, to use make this presentation, as well as fueling your spaceship. All right, that one might be a little farther down the road, but you get my point. Biofuels, the way of the future. Thank you for watching, and here are my sources.